Okay, just some post-credits on that. A couple of questions which baffled me at the time, but now, literally about an hour later, out of the stress, have managed to come up with, I think, answers for. Starting with this one, which was a nightmare. No idea what was going on. Why do we need the multiples of 17 here? Now, let's see. So, Sam writes on a whiteboard, positive integers from 1 to 6 inclusive, one of each. Now, I'm adding them up because we are trying to find the mean of all the numbers. She then adds p additional 5s, so that's p lots of 5, and q lots of 7. And the formula for the mean, we add up all the numbers, we divide by how many numbers there are. Now, there was the number 1, 2, 3, 4, 5, 6, so that's 6 numbers. There are also p lots of 5 and q lots of 7. Now, I do not know if what I'm doing is the best way of doing this, but it is the way that seemed to get to an answer. So let's sort this out. We've got 21 plus 5p plus 7q, all divided by 6 plus p plus q equals 5.3. Let's sort this out. We then have 21 plus 5p plus 7q equals, if I multiply both sides by 6 plus p plus q, that would give me 6 times 5.3 is 31.8 plus 5.3p plus 5.3q. Bit disgusting, but let's try and simplify this out. So let's bring all the p's and q's on one side, the numbers to the other. This means I'm going to end up with 1.7q, and I'm going to write it like this actually, equals 10.8 plus 0.3p. Now really here, I'm just trying to get anywhere. And actually, I don't like the decimal, so I'm actually going to times both sides by 10, just to make it a bit clearer. We now have that 17q equals 108 plus 3p. And here is where our multiples of 17 come in. There are only, at the end of the day, these 5 options for the smallest value of q. So actually, because we know that p and q are integers, and actually they're integers bigger than 1, but either way, they're integers. Because we know they're integers, they're actually, we just can try each of these out and see if they work. So, if q is 7, we've got 17 times 7, which is why we have our 17 times table here. 1, 2, 3, 4, 5, 6, 119. Now, the question is, can 119 equal 108 plus 3 lots of something? So here we have that 11 equals 3p, which is impossible because p is an integer. 11 cannot equal 3p. There's no solutions. So it cannot be that one. Now, this feels annoying. There must be a better way of doing this. But this is what it ended up coming to. So if q is 9, then we have 9 times q, which is 9 times 17, which is 153. And 153, is there a solution here? Well, here we have 45 equals 3p. And look, we have a solution. P equals 15. So P equals 15, Q equals 9, and that gives us our solution. There's no point in trying the others, because luckily we're looking for the smallest possible value of Q. And it couldn't be 7, because 7 didn't work, which means it has to be 9. So there are 9 lots of 7s, and 15 lots of 5s. Bit of a mess, but we get to an actual answer, and it wasn't that bad. Okay, the other one, now this one was a monster. This took us like 10 minutes in the speedrun, but actually can be solved really, really, really nicely. And I realized that after, once I realized the congruent thing, and that actually what we're dealing with is a bunch of similar triangles. So many similar triangles. So what I tried to do is actually work out all the lengths, but you don't need that. We've got this little triangle, this bigger triangle, this bigger triangle, and this bigger triangle, where the area is 1, 9, 16, and a mystery. But we can use scale factors here. If this length is x, because the area scale factor area scale factor is 9. The linear scale factor, the length scale factor, is the square root of that. So it's 3. The linear scale factor is 3. From here to here, the scale factor is going to be 4. So this length is going to be 4x, whereas this length was 3x. Which means, if we look here on our triangle, we have 1, 2, 3 of these lengths. This length on this big equilateral triangle is actually just these 3 lengths added up. X plus 3x plus 4x, which gives us 8x. So what we have is, from our little triangle with an area of 1 to our big triangle of area A, the linear scale factor is 8. Linear scale factor is 8. So my area scale factor is going to be 8 squared. So the area of the big thing is 64. Oh my god, so much easier than what I did. 64. So to find the area of this inner hexagon here, really all we need to do is just do the big triangle minus this, this, and this. So we just do 64 minus 1 minus 16 minus 9, which is 64 minus 26, which gives me 38, which amusingly is what I got. But this is a much, much nicer way of doing it. And actually, really, really nice question. Just had a bit of a nightmare doing it. So, hope you enjoyed the video, and look around for the next one where we look at some of my favourite questions from this paper.